Hi guys, my name is Steven, and on behalf of myself and my electronics best boy, Carl, I'd like to welcome you back to my calibration channel. I'm doing this video to support calibration guys such as myself or anybody else who's wanted to teach themselves some statistics. My first taste of statistics was when I studied for an ASQ certification that had a lot of statistics on it, and I wanted to be prepared. Also, as a calibrator, I've become interested in the measurement uncertainty that's associated with every measurement I make. And in order to achieve some kind of comfort level with that discipline, I've had to learn quite a bit of statistics. Also, over the years, I found that if I really want to understand how a tool is supposed to be used, I need to learn what was the original problem that people were trying to solve when they first invented the tool I'm about to use. That way, it's easier for me to be sure that I'm using it properly, or, hey, this is not the time to use that tool. Okay, so let's get into it. Today I want to talk about William Gosset and the creation of the student's t-Statistic. William Gosset was a guy that was hired by the Guinness Brewery in Dublin, Ireland in 1899. At the time, Guinness was the biggest brewer in the world. They wanted to add Gosset to their experimental brew team, and the responsibility of this group was to reduce or eliminate waste, control the cost of the raw materials they put in the beer, increase their throughput and efficiency, but not change the taste of the beer. People who drink beer like it to taste the same all the time, and Guinness had a good thing going. They didn't want to mess with it, but they, at the same time, they were into what we would call quality control. Now, Gosset's team was struggling with the problem of how do we make decisions about let's accept or reject Farmer Jones' wagon load of hops based on only a few samples. The essence of this problem in statistics language is the small n problem, or a small sample problem. Let me demonstrate for you how that works right here. I have here a binomial random generator. Lots of times in statistics you read about true coins. Well, suppose in 10 days someone's going to force me to bet $500,000 on whether this coin is true or not. In other words, I'm going to be on the hook for whether or not this coin is just as likely to flip a heads as a tails. Now, if I flip it 5 times, even if it's a true coin, it's not going to produce the same number of heads or tails because I've flipped an odd number, not an even number. The same would be true if I flip it 15 times. But I notice that as I flip it more and more, I've become more and more assured that it is either a true coin or not a true coin, and consequently the risk of me making a wrong decision goes down at the same time. By the time I flip this coin 1,000,001 times, I still don't have an identical number of heads or tails, but by then I know very well whether or not it's a true coin, and I'd be prepared to bet some money on it. Okay, Gosset and the brewery had the same problem. They couldn't flip a coin 1,000,000 times to decide whether to accept or reject a wagon load of hops. Yet they had to make that decision. If they were to sample their way into the normal distribution, which was the only tool available at the time, there wouldn't have been any raw materials left to brew. What Gosset did instead was very creative and very venturesome, and has come to be known as Monte Carlo simulation since he did his work. What he did was he went out and found a very large population that he knew was normally distributed. Let's say it had a population of 3,000 samples in it, but he was sure it was normal. He measured between the distance for each sample and the average of the population. Then he did it again, only did it in pairs. So he randomly combined 2 of the samples into pairs. Now he has 1,500 pairs. 1,500 times he took their average and compared it to the average of the population. He did it again for 3. Now he has 1,000 groups of 3 samples. He did the same calculation again. He did it over and over again till he had 300 groups of 10 samples. And in each case, he took the group of 10 and measured their average, compared it to the population. By the time he was through of this laborious group of calculations, he had a very good idea how much the risk went down every time you added one sample to your group. Conversely, at the end of this study, he knew exactly how much the assurance would go up if we added one sample to our group. That's what he was looking for. When he went to Guinness with this news, they were delighted. Up until now, everybody did sampling this way. Smells pretty good. Let's buy this. Or no, this is no good. In other words, it was hit or miss. Guinness now had a way to systematize the procedure for sampling the raw materials and give them a very good idea of what kind of risk they were incurring. No other brewer had this. Now, I said Guinness was delighted. Gosset wasn't quite so delighted. What he wanted was a mathematical interpretation of the behavior he'd seen in small groups. There's a mathematical formula behind the normal distribution, and here it is right here, displayed in some very, very expensive software. He didn't have that for the behavior he saw, even though he had made some important steps forward. So he said, hey Guinness, give me a year off. I want to go down to London and study with Carl Pearson. He's the foremost statistician that I know of that could help me. Guinness said, sure, take off. In that year in London, Gosset made enough progress that he was ready to publish a scientific paper. He went back up to Dublin and said, hey, good news, I'm ready to go. This time, it was the brewer that was holding back just a little bit. They said, just a second, laddie boy. After all, they were Irish. They said, look, a lot of people may be aware that you're on our brew team, and all of a sudden your name appears on the scientific paper. Suppose Joe's Brewery across town from us has a guy who happens to notice the paper, notice the author, and say, you know what? I bet we could apply Gosset's method to our problem of small samples that's been killing us. Guinness didn't want to do that because they'd invested heavily in the research necessary to produce this paper. So they arrived at a compromise. Gosset went ahead and published, but he signed his paper student. It was read by a guy named Ronald Fisher, who was just starting out what was going to be a stellar career as one of the foremost modern statisticians. When you get big like he did, you get to name stuff. So eventually what he did was name the result of Gosset's research the t-Statistic. But he said, you know what, let's name it the student's t-Statistic in honor of the guy that wrote the paper. Probably by then he knew exactly who wrote the paper. Maybe he was just being ironical. I don't know. But to this day, it's known as the student t distribution and the student t statistic. Now I said that Fisher picked up Gosset's idea. He recognized how very powerful it was right away. For example, Gosset's method is a way of determining statistical significance. In other words, you take a few samples of Farmer Jones' wagon load of hops. You see a little bit of difference, or you see some difference between your samples. Is that sample significant given the number of samples that you drew? Well, Gosset pointed the way towards figuring out, are these statistically significant differences, or is this just the kind of variation you'd see in any population, large or small? As I said, Fisher took these ideas and ran with them. He was very honest, and of course he gave credit where it was due. But some statisticians have said that he took things too far eventually. So that'll be the subject for another video. On behalf of my makeup guy, Carl, and myself, I want to thank you for the time you spent watching this video. I hope you found it helpful. I enjoyed making it, and I'm enjoying making a whole bunch of videos for calibration people that I hope you'll stick around for. In the meantime, thank you.